If it's okay with you, I'd actually kind of like to deviate a bit and probe more your thoughts about information and black holes because, as I mentioned before we spoke, I talked yesterday to Eric Verlinde, who is a string theorist in Holland, and we were talking about holography and how the information contained in a black hole is not, on his view or on many string theorists' view, it's not encoded in this singularity at the center, but it's encoded in, I guess, Planck area units on the surface area of the black hole. And some string theorists, I think Leonard Susskind is the main name that comes to mind, believe that we live in a holographic universe, and that, and this is moving a bit beyond black holes, but everything we experience in the bulk, the center of the universe, is really a projection from a two-dimensional boundary on the outside of the universe. And I'm wondering, when you think of black holes, do you still have this view inspired by general relativity where the information really is encoded in the singularity, there is a singularity there, or if this idea of a hologram resonates with you?
Well, you see, I mean, this touches on a number of kind of deeper topics, which you may or may not want to get into. But I, although I in my, my day job has been very much in climate, the one area I have put quite a lot of effort into in the last, couple of decades, actually, is trying to understand the meaning behind what's called the experimental violation of Bell's inequality. And I have formed a very definite view on this, which is that, you see, the problem is with Bell's inequality. This is the experiment which won three eminent physicists the Nobel Prize this year. So it's an experimentally proven result, but the question is, what does it mean? And it seems to kind of go against Einstein's belief that the world is deterministic. God doesn't play dice, and moreover, that the world doesn't have what he calls spooky action at a distance, which is usually used. The word used is non-local. So non-locality or actually indeterminism are both, I think, uncomfortable ideas. I mean, non-locality is certainly a very uncomfortable idea. Now, quantum mechanics itself kind of gets around that because the state vector in quantum mechanics can describe superpositions. So it kind of evades Bell's theorem because it's not really deterministic in the normal sense of the word, or realistic, I think, is the word which most people would use. So I'm very of the view that actually there is another way out of Bell's theorem, which is to do with something called superdeterminism, and it's often ridiculed as implying some ridiculous conspiracy. But I think and I've written a paper recently on this in the archive, so people can look at it if they're interested, that actually it reflects the fact that the laws of physics are actually much more holistic. And fractal attractors are a good illustration of a kind of holistic geometry. The point about this is that I think there is a way, for me, this points to a way for a kind of potential successor to quantum mechanics, to quantum theory, and that we shouldn't treat quantum mechanics and quantum theory as kind of inviolate and, almost biblical in its correctness, let's say. Now, the point about this is that most, I think, of the people who, look at the black hole problem from this holographic string theoretic kind of perspective, very much do treat quantum mechanics as a given that is not, is not open to violation. So, because I don't believe that personally, and I come to it very much from this Bell theorem perspective, I'm not particularly driven to the holographic principle, or indeed anything that absolutely says all information has to be kind of preserved in an inviolate way. I don't come to that as a principle that absolutely has to be upheld. So I would say I am more of a kind of traditionalist in that respect, that I do see the entropy of the black hole is somehow contained in the micro degrees of freedom at the singularity, and not particularly at the horizon. I mean, the horizon is a very undefined quantity, by the way, locally undefined. I mean, all a horizon is it's the surface that just fails to reach, or where light signals just fail to diverge out to infinity. So if I threw a big rock into the black hole 100 years into the future, that would change where the event horizon is today. So there's no way of knowing where the event horizon is today. It's completely, it's undefined at a local level. So I find it very hard to understand how one can formulate notions of entropy and so on in terms of horizon properties. So it's a long answer, but I'm more of a, I'd say, call it traditional GR person in that respect.
I'm really glad that we went down this route. Is it okay if I pursue it a little farther? Okay, great. Yeah. So yesterday, Eric confirmed exactly what you said, in that he told me string theorists believe the world is fundamentally quantum mechanical. So I can understand how, if you are going to deny that premise, it's not going to lead you to holography. I understand. I mean, I know much more about Bell's theorem than I do about superdeterminism as a view. So Bell's theorem rules out local hidden variables, but there are, of course.
Well, you say that. You see, it doesn't. It rules out local hidden variable theories if you make this additional assumption, which is called sometimes called measurement independence. It's sometimes called statistical independence. Sometimes called lambda independence. Goes from different names. And, in the early days, some of the philosophers of physics, Abner Shimoni, I think, was most well known for this, made the comment that, wouldn't this mean if we violated measurement independence? If you like, I can explain exactly what measurement independence is, but we might be going down a rabbit hole that you don't want to go down. But the point is, he said, well, wouldn't that kind of, isn't that like doing a kind of a drug trial where somebody behind the scenes is manipulating, which person gets which drug, so you end up with kind of statistics that aren't somehow reliable. And for some reason, that picture has, that's the picture everybody thinks is what is being implied by if you violate this measurement independence assumption. But I've spent a long time, believe me, thinking about this, particularly in relation to chaos theory and fractal attractors. And I'm totally and utterly convinced that this is not correct, that there's a perfectly sort of sensible, logical, feasible, plausible way of explaining this violation of measurement independence without having to invoke any of these kind of weird conspiracies, as they're called. The point about that is that there is, therefore, a way to understand the violation of Bell inequalities without having to give up on either determinism or locality. I should say, I think Bell himself kind of half understood this, and reading his papers, he was kind of grappling towards this, I think, without quite seeing, what was going on. But, I'm happy to debate this with anyone. But I was to say, you may not want to go down this too deeply at this stage.
No, so what I should have said was the conventional view, and I think that this is true, is that Bell's theorem rules out local hidden variables and results if someone still thinks QM is incomplete, if they want to preserve or use hidden variables, it pushes them to adopt something like Bohmian mechanics. But what I wanted to ask you is, because I don't really know much about superdeterminism, I think what comes to mind is that it somehow it avoids non-locality by positing that what we see as spooky action at a distance is something that was determined locally but long in the past. And I'm wondering if that is how you would explain it, maybe, and why it suggests that to you that quantum theory is not the final theory, and then we can move on to the primacy of doubt, if that's okay.
Well, you see, I'm struggling to sort of explain this in a way where I don't get involved in technical details, which I don't think will interest people in detail. But for a long time in the past, just to follow my career. So I moved into weather and climate. You ask me whether the mathematics of general relativity is relevant to weather and climate. The answer is yes, to some extent. But what I discovered, and that's why I've gone back to theoretical physics, in the last few years, not full time but part time, is because the mathematics, and in particular the geometry of chaos theory, which underpins a lot of weather and climate stuff, is super relevant to these questions that we're talking about. The idea of let me just see if I can describe. I mean, a chaotic attractor. You take the equations, they're ordinary like differential equations of chaotic systems, and you run them on a computer, and you look at the behavior of the variables in what's called state space. So the state, or the space spanned by the variables. So if there are three variables like there are in Ed Lorentz's kind of prototypical chaos model, the equations trace out this fantastic geometry in the three dimensions of the three variables. And I mean, Lorentz's great insight, which took him a long time to get to, was that this geometry that these equations are tracing out is an example of a fractal, or a kind of what's called a Cantor set sometimes, or a fractal. And the difference between a fractal and a kind of simple Euclidean geometry is that the fractal has structure which persists under a zoom. You can zoom into a fractal and you see more structure, and you zoom in again, you see yet more structure, and so on. Whereas something like a sphere, if you zoom into the surface of a sphere, it just ends up looking boring and flat. So something quite fundamentally different. Now, the idea is, if you imagine a dynamical system that is evolving precisely on one of these attractors, and you imagine freezing it in time, and then you say, well, what would have happened if I changed one of the variables very slightly, keeping the other two variables fixed? What you find is you almost certainly move off the attractor altogether. You move into a little gap in the fractal. So a small mathematical perturbation takes you into one of the gaps. Now, when you're proving Bell's theorem, this is exactly the type of question that you have to ask yourself. You say, Alice and Bob measured a particular pair of particles, and they got definite results, up or down for their measurements. But in order to show that your theory satisfies this Bell inequality, you have to ask the question, what would Alice and Bob have seen if they measured those same particles with different measurement settings. So if Alice changed her measurement setting and Bob kept it fixed. And measurement independence says that, they would have just got another set of results, kind of unrelated to the first results. But if physics operates on this kind of holistic geometry, which is the way I like to think about it, then that counterfactual experiment, the one that they didn't do but they might have done, where Alice measured her particle differently, according to the kind of chaos geometry idea, would lie in a gap in the fractal. So it would be actually mathematically undefined. It's not that they get different results, but that counterfactual experiment that you need to prove Bell's inequality would be actually inconsistent with your laws of physics. Now, just to make one last point, the interesting thing about this idea of fractal geometry is that all points on it are sort of equally important or equally, integral to the geometry. So although it's a deterministic system, it's not that somehow there's an initial condition which is more fundamental than any other point. That's the normal way we think about initial conditions. Say, the Big Bang was the fundamental initial condition from which everything else sprung. That's not the way it works with these fractal geometries. In some sense, every point has the same ontological status as every other point. And that's a really it's an unusual conceptual, I think, perspective that it gives you. So it doesn't single out, the Big Bang as being kind of somehow special. All points on the attractor are equally special and important. So anyway, that's my, that's very strongly my view. I wanted to say, by the way, if anyone's particularly interested in the gory details, I've written a paper called Superdeterminism Without Conspiracy, which you can find on the archive in the quantum physics, quant PH section of the archive. And so I go into all the details there if people are interested.
This sort of reasoning you're describing, the counterfactual reasoning with Alice and Bob, it actually reminds me very much of the sort of reasoning in the EPR paper that provoked Gauss' theorem.
That's absolutely right. Every single no-go theorem in quantum mechanics involves counterfactual reasoning. Absolutely every single one. So the status of counterfactual experiments in terms of your theory of physics is absolutely 100% critical. This is the single biggest issue which I want to try and get over. We do the real world, works, things happen. We have a theory which hopefully can explain things that happen. But theories, the very nature of theories is that you can change variables and see what would happen if other things were different. However, it may be, and this is the case, I believe, in quantum physics, that some of those changes that you make, which you might think, why not make the change to a variable? It's perfectly reasonable. But actually, there are constraints, these geometric constraints in state space that say that some perturbations you make to variables that are counterfactual actually violate your laws of physics. And that, for me, is the crucial thing for trying to understand all of these quantum no-go theorems. So you're absolutely right. It started with EPR, continues through Bell, everything else, GHZ, Wigner's friend, which is a lot of the modern stuff is based on things called Wigner's friend. It just does your head in.
David Deutsch.
If you look at it. Have you come across that? I don't know.
Yeah, it's David Deutsch's thought experiment, right? Or am I?
Well, no, it went back to Wigner. So you have you do a quantum mechanical experiment. So Wigner's friend. This is Eugene Wigner, very eminent 1950s, 60s physicist. He had this experiment where his friend was doing a quantum measurement in a box. And the question is, Wigner is outside let's say a box. I mean, let's say a room or something which is completely sort of shielded from the outside. So Wigner's outside the room. And the question is, how do you represent the quantum state of the quantum system plus the friend who has done the measurement? So is that in a superposition as well until Wigner himself opens the door and observes that the friend has observed the quantum state to have gone to one of the measurement eigenstates or a different one? And if you believe that, then you can run into, this is all the latest stuff, you can run into problems that what you believe to be a kind of an unassailable fact of the world is actually observer dependent. Different observers can come up with different conclusions about whether, the value of experimental results. Now that's completely bonkers, right? However, to get to that conclusion, you have to assume this measurement independence, that you can talk about counterfactual experiments. And again, if you don't accept that, which I don't accept that, then that stops you reaching these kind of nonsensical conclusions that, facts of the matter are what we think of as absolute facts of the matter are observer dependent. So it rules that out. As long as if you rule out complete counterfactual definiteness, then you don't have a problem with these crazy no-go theorems. They're not so paradoxical after all.